Hi everyone. Today I'd like to explain about the monotone convergence theorem. Using this monotone convergence theorem, we are going to solve the two very important problems. That is the sequence 2 raised to n by n factorial. We have to show that this is convergent and find its limit. And also we have to show that limit n tends to infinity r raised to n equal to 0 for a mod r less than 1. Otherwise it is divergent. That is we are going to discuss. Before that, what was the monotone convergence theorem? Monotone convergence theorem was every bounded monotonic sequence is convergent. That means we can say that a bounded above plus an increasing or bounded below plus decreasing. Then also we can see that the sequences converge. Okay. So using these we are going to do some more problems in this. Right. So consider the first problem. Show that 2 raised to n divided by n factorial. This is the sequence. And I like to explain that. So I like to show that the sequence is convergent. I like to show that the sequence is convergent. So that what was here an equal to 2 raised to n divided by n factorial, and an plus 1 equal to 2 raised to n plus 1 divided by n plus 1 factorial. Okay, so a1 equal to what? A1 equal to 2, a2 equal to 2, a3 equal to is approximately same as 1.3333, a4 is same as 0.66667, a5 is approximately 0.26667, a6 is approximately same as 0.088889, and a10 etc. a10 is approximately 0.00282 and like that, right? And these type of in this type here this ANs are approaches and AN is greater than or equal to 0. We can see that this is always positive since this is 2 raised to n divided by n factorial. This is always positive, and we know that, and we can say that this is always greater than or equal to 0. So this is bounded below by the value 0. So this is the sequence is bounded below by 0, the value 0. And also we have to show that this is increasing or decreasing. I like to show that this is consider what was this? an equal to 2 raised to n divided by n factorial, and an plus 1 equal to 2 raised to n plus 1 divided by n plus 1 factorial, and an plus 1 divided by an equal to 2 raised to n plus 1 divided by n plus 1 factorial. Divided by means 2 raised to n divided n factorial divided by 2 raised to n. This 2 get cancelled and this is equal to 2 by n plus 1. This is 2 by n plus 1. When this is equal to, so an plus 1 is divided by an is equal to 2 divided by n plus 1. When n equal to 1, this is 1. N equal to 2, 3, etc. N equal to 2, this is equal to 2 by 3. Next n equal to 4, that is 2 by 5, 2 by 6, 2 by 3, 2 by 7, etc. So this term is always, this ratio is less than or equal to 1 for n greater than or equal to 1. This is always less than or equal to 1, which implies that what we have got, this is less than or equal to an for all n greater than or equal to 1. That means an plus 1 is less than or equal to an. This means the sequence an is decreasing sequence. Sequence an is decreasing sequence. Okay, so what we have got, that is sequence an is decreasing and bounded below, which implies by monotone convergence theorem for the sequence, we can say that the sequence is convergent. The sequence is convergent. Okay. So using this, we have proved that this is convergent. Next, we have to evaluate the limit of this. So limit, suppose that limit n tends to infinity, an equal to some l. Then if n tends to infinity, an equal to n, then limit n tends to infinity, an plus 1 also must be same as l. So consider this value. So limit n tends to infinity, an plus 1 equal to limit n tends to infinity 2 by n plus 1 into an. Okay. So we have this is L equal to limit n tends to infinity 2 by n plus 1 into limit of an, that is L again. What is this? As n tends to infinity, this term goes to 0. So this is equal to 0 into L, which implies L equal to 0. That means limit n tends to infinity, an equal to 0. That's equal to limit n tends to infinity, an equal to 0. So the limit exists and the limit is equal to 0. Right? This is a problem using this monotone convergence theorem. Also, they have done in another way also. You look through the textbook also. So we can solve this also. Right. Next is very important theorem. Very, very important one. That is show that limit n tends to infinity, r raised to n is equal to 0. Show that limit n tends to infinity, r raised to n equal to 0 if mod r less than 1. So the solution is, if r equal to 0, then each term of the sequence is equal to 0. Right? So we are doing this in r equal to 1, in between -1 to 1, and when r equal to 0, this way we are doing that, right? So if r equal to 0, each term of the sequence is equal to 0, right? So then there is nothing to prove, right? The sequence converges to 0, and so suppose that 0 less than mod r less than 1, right? Then 1 by mod r is equal to what? 1 by mod r is greater than 1. Therefore, there exists a positive number p such that 1 by mod r equal to 1 plus p equal to 1 plus because this 1 by mod r is greater than 1. So we have 1 plus p whole raised to n is equal to what? 1 by binomial expansion n into n minus 1 divided by 2 factorial into p square plus etc. plus p raised to n. And we know that which is greater than or equal to here, which is this is greater than all the term. This is a NP. NP, when you add 1 and other terms, this term will be greater than NP. So we can easily say that this is greater than NP, right? So first of all, I like to explain that that is, we have done this solution in two or more cases. If r equal to 0, first of all, we have to check when what happened if r equal to 0. Then we can see that this sequence is completely all the terms of the sequence is 0. Then nothing to prove. Then sequence converges to 0, right? So that we move on to the next case. So that is 0 less than mod r less than 1, right? And from this, I can take this mod r to the right side. Then what will happen? 1 divided by mod r. On the left side, there is 1. 1 is remaining, right? So 1 by mod r is greater than 1. Okay. So there exists a positive number p such that 1 by mod r is greater than 1 means 1 plus, suppose it is 1.5. So I can write this as 1 plus 0.5. That 0.5 is the p, right? If it is 2.7, then I can write this as 1 plus 1.7. 1.7 is the positive number. Okay. So using binomial expansion, we can expand this and we can see that this is greater than n into p. So 0 less than mod r raised to n is equal to 1 divided by 1 plus p whole raised to n, which is less than 1 by n into p. Okay. And we have limit n tends to infinity, 1 by np is equal to 0. So by Squeeze theorem, this is equal to r raised to n is equal to 0. Right? This is equal to 0. So 0 less than mod r raised to n less than 0. Then limit of r raised to n is equal to mod r raised to n equal to 0 by Squeeze theorem. Right? Okay. So this is the result of this, and also we can see some properties of the sequence, and this is convergency, mod r less than or equal to 1 and mod r strictly less than 1, and if r equal to 1, this converges to 1. So in this interval minus 1 strictly less than or less than or equal to 1, then limit is exists and the value is this one. For all other values of r, the limit the sequence diverges. Okay. So next is we have to do some more exercises in this, right? Proof of the theorem monotone convergence theorem is omitted. So next is we have to do some more problems from the exercises. In the next video, we can discuss that. Okay. So thank you.